Hey everybody, welcome to Kicking the Tires Journey to Building a Harvester Test Framework session. My name is Guang Yee, and I'm a member of SUSE Cloud Solutions team. Our team is primarily responsible for supporting SUSE OpenStack Cloud for both Cloud Lifecycle Manager and Crowbar. My data center infrastructure journey began with Opsware, which was best known for its server automation solutions at the time. I then went on to work on public and private cloud projects, which were based on open source OpenStack cloud platforms at HP. After the SUSE acquisition of HP's cloud business unit, I transitioned over to SUSE and we became SUSE OpenStack Cloud. Throughout my journey, automation in many ways has been an integral part of my work. In early 2021, I, along with three of my colleagues from SUSE Cloud Solutions, got an opportunity to work on the Harvester project as a part of the volunteer program. Because of our experience in automation, we were tasked to come up with a framework to automate the Harvester functional test cases. And I serve as the technical lead for the Harvester test automation. In this session, I will take you through our journey with challenges we were facing and the solutions that we came up with. But before we get into that, we'll do a quick introduction on Harvester for those who are not familiar with it. Then we'll dive right into the challenges and solutions, such as automating Harvester bare metal provisioning, creating a test framework to automate the Harvester functional tests, automating, automating running the functional tests on the daily basis, and how to increase engineers' velocity so that we can be more productive and efficient. And lastly, create a CI for the Harvester installer repo. At the end, I'll share some of my takeaways from our test automation journey. So, what is Harvester? Harvester is an open source hyperconverged infrastructure, or HCI, software built on Kubernetes. As such, it supports Kubernetes REST APIs. Having open source APIs is important for test automation. Under the hood, Harvester utilizes Rancher for identity management, authentication, authorization, and cluster management. It uses Longhorn for distributed block storage. The cool thing about Longhorn is that it turns the local server storage into logical volumes that are distributed and replicated for higher availability. Harvester uses KubeVirt for virtual machine lifecycle management, such as creating, starting, stopping, pausing, and deleting VMs. It supports Cloud Init for SSH key injection and VM configuration. It supports serial console access and live migration. And for networking, Harvester supports multiple network interfaces, VLANs, and NIC bonding. VM data can be backed up to or restored from NFS or S3 buckets. It supports Harvester Terraform Provider, which is important for automation using infrastructure as code. Harvester is tightly integrated with Rancher for multi-cluster management. For example, you can import multiple Harvester clusters into Rancher and manage them all centrally. You can easily achieve multi-tenancy by assigning the appropriate security policies for accessing those clusters. For the cool part about Rancher integration is that Harvester is also a cloud provider for Rancher, or in this case, Node driver. In other words, you can create a Rancher driver on top of using the Harvester VMs. Harvester also has built-in monitoring integration with Prometheus and Grafana. For installation, Harvester provides ISO images. It also provides kernel, RAM disk, and rootfs images for Pixie or iPixie boot. It also supports air-gap environment where internet access is not possible. So I borrowed this architecture diagram from the official Harvester online documentation. As shown in the diagram, Harvester is running on all the bare metal nodes. As mentioned earlier, it uses Longhorn for storage management and KubeVirt for VM lifecycle management. The VMs can either use the default network or the VLAN networks, or both. Harvester automatically support higher availability when, or HA in this case, when the cluster has at least 3 nodes. The promotion of the management nodes are all handled automatically when there are enough nodes to form a highly available cluster. Just to be aware that in order to avoid a split brain situation, a HA cluster should have should have odd number of nodes. But that's something that the users don't have to worry about. That's all handled internally by Harvester. Now, onto our journey. When we first joined the Harvester team, our first challenge was to come up with a framework to automatically provision Harvester to the bare metal servers in our lab. Our lab was basically made up of individual isolated bare metal environments, each with the number of bare metal servers allocated. Our goal was to enable QA engineers to deploy a Harvester cluster onto a selected bare metal environment at the push of a button. Ideally, a QA engineer would just need to first reserve the environment, then select the Harvester versions that he wants to deploy, the cluster size, and then press the button to kick off the deployment. When the deployment is completed, the team will get a notification. As mentioned earlier, our lab is made up of individual isolated environments. Each environment is allocated with a number of bare metal servers. Although the servers are not evenly allocated among all the environments, some environments may have more servers than the others. And the only way to access an environment is through its deployer server, which is connected to the provisioning, or in this case, the ILO network. Each environment also have a number of VLANs allocated. Those VLANs are pre-configured at the physical switch. The deployer for each environment are accessible from the local area network. So what's our solution? We end up using Jenkins, Ansible, and Redfish. So why use Jenkins? Well, our team was quite familiar with Jenkins to begin with, since we have been using it for years. We don't need much of a learning curve in this area, which was very important for a fast-paced moving project like Harvester. To satisfy the repeatability and recreatability aspects, we ended up running Jenkins in a customized container and utilized the Jenkins configuration as code plugin to configure Jenkins. That way, if we ever have to recreate the Jenkins node, the Jenkins environment for whatever reason, we simply recreate the Jenkins container. The drawback with this approach is that the Jenkins environment is highly static, which means is that we'll need to rebuild the container every time we need to change the configuration, like adding or updating a job or credential. Why use Ansible? Well, again, our team is well versed in Ansible because we have been using it in SUSE OpenStack Cloud for provisioning. Ansible playbooks are reusable, which we'll see which we'll see why later on. Also, our lab environment configurations are stored in YAML files, which make it easier to load them into Ansible as variables. And we can use Ansible Vault to encrypt any sensitive information like idle passwords or any other types of credentials. All our jobs are orchestrated using Ansible playbooks. A Jenkins job would simply just use the Ansible plugin to run the appropriate playbooks to perform those tasks. Right, Redfish. Well, that's the easy one because all our bare metal servers in our lab support the Redfish API. And the Ansible Redfish module mostly works for us. Although we did find in some instance there was some incompatibility between Ansible Redfish module and some of our HPDL 360 servers in our lab. So apparently HPDL 360's implementation is slightly different from the rest of from the outside world Redfish implementation. But we managed to work around that just by using Redfish API directly from the shell module. Basically, use the curl command to call those APIs. As this diagram shows, we deploy Jenkins as a container in our Jenkins node. When a job is executed against a selected environment, it uses Ansible plugin to run a playbook, which targets the deployer of that environment. The inventory is dynamically constructed using the environment's YAML configuration files. Now let's walk through the play to see how it works. First is set up the appropriate SSH keys on the deployer so that the owners can log into the environment. Then we make sure the iPXE boot environment is pristine by updating the HTTP, DHCP, and TFTP components on the deployer. The next step is to download the correct versions of the Harvester ISO images onto the deployer. Then it uses the Ansible templates to configure iPXE boot files by updating them with the locations of those images, along with each of the bare metal servers configurations, like the network interface names, MAC addresses, and things like that. Prior to installing the Harvester, we want to make sure all the servers are in the power off state. So in this case, we just use the Redfish APIs to power them off. The play will then go on to set the boot options for each of those servers to use Pixie Boot as the next boot option. Which means is that next time when those servers boot up, it will use Pixie Boot instead of the local disk. Then we're ready to install Harvester. To install the cluster, we need to first boot up the founders node in the cluster in the create mode, and wait till is completed and operational. And for the remaining nodes in the cluster, we boot them up one by one and in the joint mode and have them join the cluster. The health checks are done by pinging the node's API endpoint over HTTPS. When all the nodes are healthy, the installation is successfully completed. Otherwise, we have a failed installation. In either case, the last step of the play is to notify the team Slack channel on the installation status. So after automating bare metal provisioning, we need to turn our attention to the next challenge, which is to come up with a framework to automate the functional tests themselves. At that time, the functional tests were done manually from Harvester Web GUI, which was very time consuming, which was a very time consuming process. The tests, we also categorized the tests according to their to the feature groups like virtual machines, volumes, images, networks, and so on. We have both positive and negative test cases, and each test case were assigned a priority, like P1 for highest priority, and P2 for the next higher priority, and so on. Some tests were destructive by design, and they were not reversible. For example, if a test remove a node from Harvester, and at the end of that test, the cluster would end up with one last node. So that could be a problem if we have more tests to run after that. And we want to create a test framework so that QA developers can easily develop and automate the test case. And the framework must also support test classifications and prioritizations so that we can selectively run those tests based on their category and priority. For example, if we want to run tests that removes a node, we want to run the test that removes a node last so that it doesn't impact all the tests that come after that. And for this one, we opted to go with the pipe test framework, and it has all the capabilities that we were looking for. With our background in OpenStack development, we were quite familiar with it to begin with. So there's no learning curve for us. Since we were automating functional tests, or black box testing in this case, using Kubernetes API works just fine for us. With PyTest, we can utilize the markers for test classification and prioritization to enforce running those tests in predetermined order. We were able to use PyTest ordering library for that. We make extensive use of fixtures, especially for setting up Harvester resources like nodes, VMs, images, volumes, networks, and so on. And the fixtures allows the test to share common state, which makes the test cases much simpler to implement and the test code much easier to comprehend. Now, the use of Kubernetes APIs was a big challenge for us since none of us were familiar with it. We were hoping to find a Python KubeVirt or Kubernetes client library out there that is intuitive to use, with good documentations and good examples. Unfortunately, we didn't find any. So we decided to just build our own by just using Python request library. We use a simple retry strategy to improve session resiliency, like retried on network connection errors and HTTP 500 proxy errors and so on. It took us a while to get used to the Kubernetes APIs. Initially, the generated Swagger API doc was pretty difficult to follow. The API payloads were incredibly complex with lots of boilerplate YAML code. So it really doesn't really make sense for us to build those YAML codes from scratch in our test code. So we managed to solve that problem by first capturing the API payload from the browsers using the web developer tool from the Harvester Web GUI. Then we templatize those payload using Ginger 2 templates. We only parameterize the fields that need to be updated and leave the rest of them as is. The problem with dealing with Kubernetes APIs was that we also often run into HTTP. I mean, the other problem that dealing with Kubernetes API was that we often ran into HTTP 409 request conflict when we're trying to update a resource. When that happens, we pretty much have to, first look up the latest versions of that resource, and then apply our changes on top of that, and then keep trying until the resource can be updated. And luckily, the Python polling tool library was perfect for this one. Our test framework is a I have included a link here in case you want to take a peek at our test framework and how it works. And if you are interested in contribute to it, please feel free. It's open source. So as more and more tests have been automated, at a point we will need to run the entire test suite on a nightly basis instead of running them individually by QA engineers from their own command line. So we also want to generate a nightly test report at the end and post the test results to our team's Slack channel so developers can be alerted on any regressions. And for this one, the solution was relatively straightforward. We basically create a daily Jenkins job and use a dedicated environments to run those tests. By using Ansible earlier to automate the bare metal provisioning, we were able to reuse some of those playbooks for this job. All we have to do is just create a new playbook to execute the test suite and generate the test report. As shown in the diagram, the first part of the job is basically bare metal provisioning. So that part we can pretty much reuse the Ansible playbooks that we had earlier. Once the Harvester cluster is ready, the job will then run the test playbook to first clone the test repo, and then configure the test, and then run the functional test and generate the test report at the end. At the last stage, the test result is posted to our team Slack channel. So what else is left to do? Well, we have another problem. Resource constraint was slowing us down. It turns out we have limited bare metal environments when some of the environments got dedicated for the nightly jobs. Also, whenever we encounter a failure that needs to wait for the domain experts to investigate, we have to freeze that environment, or preserving the crime scene, as some of us would call it. Having QA engineering share an environment that was also not ideal because they could inadvertently step in on each other. So we really want to find a solution such that anyone can stand up a disposable Harvester cluster on their own development environment, like on their own desktop or laptop. So what do? We virtualize Harvester. We were able to accomplish that with Vagrant. Vagrant Ansible provisioner, and Vagrant libvirt KVM provider. And this is my favorite solution, by the way. We chose Vagrant for a number of reasons. Vagrant environments are disposable and repeatable. Developers can easily run it on their own desktop or laptop. And Vagrant supports no box or Pixie boot. And the libvirt KVM provider works well for us, and it has a ton of configurable options. As an added bonus, by using Ansible Provisioner, we were able to leverage some of the Ansible playbooks we created earlier for our bare metal provisioning. All the Vagrant boxes are configurable, and the configuration for the Harvester cluster is pretty simple. And I have included a link to the Vagrant Harvester repo if you want to check it out. It's in GitHub under Harvester iPixie examples. So let's walk through the diagram to see how it works. We first boot up the iPixie Vagrant box and configure all the pieces required for iPixie boot, and that includes setting up DHCP, HTTP, and TFTP, downloading the correct Harvester images, and updating the iPixie configuration file. Right? Does that sound familiar? Well, those were the same sequence for bare metal provisioning that we talked about earlier. So we were able to reuse that Ansible playbook here. We also instruct Vagrant to create a private boot network and not use the standard Vagrant DHCP server. Once the iPixie Vagrant is up and running, we'll then boot up the first Harvester Vagrant node on that private boot network. So instead of talking to the default Vagrant DHCP server, it will now talk to the DHCP on the iPixie Vagrant node to initiate the iPixie boot. Once the first Harvester node is up and running, we'll then use the same mechanism to boot up the remaining Harvester Vagrant nodes and have them join the cluster. The creation of Harvester Vagrant gave us the tool to tackle the last challenge, which was to create a CI for Harvester installer. Early on, we often ran into a fundamental installation problem. We often ran into some fundamental installation failures because the project was moving very fast. So when an ISO image failed to install, sometimes we lost productivity while waiting for the problem to be fixed. Because our installation domain experts are half of the world away. So it would be nice to have a CI for Harvester installer so that we can catch those potential problems prior to merging changes to the repo. As Harvester is open source, the CI must be publicly accessible as well. For security reasons, we can't host a CI inside the SUSE internal network. There's no ingress into the SUSE internal network. Luckily, the Harvest team were able to obtain 2 Econex bare metal nodes for our CI. We simply provision Jenkins on those nodes, one master node and one agent node. And we decided to use Harvester Vagrant to test the installation since we don't need a large nodes to run that. And it should catch the most common installation failures. But with a limited time and resource, we were not able to test all the permutations of the configuration or the config options for the installer. Likewise, with this approach, it may not catch all the corner cases, like compatibility issues with the vendor-specific firmware, for example. As shown in the diagram, the job is triggered by a webhook whenever a pull request is created or updated against the Harvester installer repo. The job can be executed on either the master node or the agent node, depends on the load distribution. The job uses Ansible plugin to run an Ansible playbook, which does the following. Like it shows in the diagram, it will first check out the pull request branch from Harvester installer. It will then build the artifacts like the ISO images or the images for the Pixie boot. The next text, the I mean the next task is to make sure that the environment is pristine. In this case, if you have leftovers from the previous job, it will then proceed to update the Vagrant configurations with the locations of the newly built images, and then kick off a Harvester Vagrant installation. The results of the installation is then posted back to to GitHub, uh, whether the pull request is good or no good. The last task is to clean up the environment. So our takeaways. It was very exciting for us, coming from OpenStack background, to have a window of opportunity to work on hyper converged infrastructure like Harvester, and be able to contribute to it. I was very impressed with what Harvester brings to the table. It's a really cool product, and we also got the experience with Kubernetes APIs. Not sure if I like the complexity, um, but we know enough to be dangerous. um, the other important takeaway is that when working on the fast-paced project like Harvester, it's okay to use your experience and to make thin slice decisions instead of spending time worrying about things like any best finding the best solutions out there. Just go with what's been working for you. For example, using Jenkins may not be new, or Jenkins may not be new or trendy, but it got the job done for us, and we didn't have to worry about any learning curve. Lastly, again, for a fast-paced project like Harvester, um, we managed to avoid unnecessary complexities. Developers often spend way too much time worried about things like future proof or technical depth, in searching of a comprehensive feature-rich solution, to a simple problem. Take bare metal provisioning, for example. There are plenty of comprehensive frameworks out there like OpenStack Ironic, Crowbar, Cobbler, and etc. But they were way more than what we needed. So a simple Ansible play would work well for us. With that, I want to thank you for attending the session. Please feel free to watch. Please feel free to reach out if you have any questions. Thank you.